Yeah, okay. So we will do these four things. So let's do the interpolation example. So for the interpolation example, we will use sin x, okay, a function of sin x as an example. Okay, so let me go to the Matlab. Can you see the Matlab?
Yes.
Okay, let me clear the screen. Okay, so for interpolation example with Matlab. Okay, so what I want is I want to plot. So for example, if we have a, just as an example, okay, if we have mm, data points, x, y data points, where y is the function sine of x, okay. So if we have x as some data points from 0 to 2 times pi, okay. I want that interval to be about pi by 4, okay. Pi divided by 4 x values. So if we have x values something like this, yeah, 0 at a 0, the next value is pi by 4, the next value will be pi by 2, and then up to 2 pi, okay. And then we have y values as sine of x, okay. And then if I want to plot it, plot x versus y, okay, then I can plot it. So let me save this small script as the plot sine x in lab, okay, sine x lab, okay, plot sine x lab. Let me make it plot x lab, okay, plot sine x lab. That's this. And let me run this script. So I will run this script and it will plot this, okay, it will plot it like this, right. You can see that this plot is not very smooth because Matlab is assuming the connection between these points as lines, okay. I can just close it, and then I can just show only the markers. So for showing only the markers, I use O as for the markers, and then I can run this command again. This command again, and then I can see that now I can only see these markers over here. So you can see the markers over here, okay. That's it. Okay, so what I can want to know is what I want to do. Okay, let me run again. I just closed it unexpectedly. So what is my next step? My next step is that I want to interpolate it between, these are the given points. Suppose these are the given points. I want to interpolate these points between them. So for this, I can use interp1 function in Matlab. Okay, interp1 function in Matlab. So for that interp1 function in Matlab, I need some new x values. So I can say that these are the xx values, okay, xx values. And these I take, maybe you can, it's up to you, but we can take any value. So for example, if I want to interpolate it some certain values, so maybe I can take these values from 0 to 2 times pi. Okay, 0 to 2 times pi's, and but I want these values to be about 100 values. So therefore, I can use this command linspace. Okay, linspace 0 to 2 pi. So in this case, I will get about 100 values of x from 0 to 2 pi. Okay, so the data will be quite smooth in this case. And in this case, the new y values will be the sign of these xx values. Okay, but in this case, these are the original values. Okay, but what I want is that the new y values I want as the interpolated values. Okay, so for the interpolated values, then I will use the interp one function. So it is interp interp, and then this is not L, this is one interp one function, and then I will enter for the interp one the x range values. So x range values are these x values, and the y range values are these y values. Okay, and where I want these values to be interpolated for these new xx values. Okay, for these new xx values, and then I will close it. Okay, and in this way I will get these values. So now let's see if I want to plot it. So then how does this plot look like? So plot of xx versus yy. How does this plot look like? How does this plot look like? So I want to show this plot as a maybe red line. Okay, red line. Okay, for red line I will use this R in the inverted commas over here. So this R is showing that I will show it with the red lines, and I will close it. So now I will run this code. Run. Okay, I got some error. So error in linspace line 15. Linspace. What is this? Why is this error? Line 4. Oh, okay. Yeah. In this case, 0, comma. Okay, should be not be colon over here. Yeah, I think in linspace the error. Okay, now I run it. Okay, so it has run, and then I think the plot, it has plotted it. So I need for showing the plot, I will go over here. So here, yeah, I think I will need to close it and run again. Okay. So I have got this plot. So this is the plot for the xx and yy. Okay, but I cannot see the previous plot in which this I have this original values. So I think I need to add one more command over here, hold on. Okay, hold on. This will mean that the new plot will be plotted over the older plot over here. Okay, and then I can now do it. and then plot. Yeah, so now I can see that I get these values over here. So as you can see that these markers show the x and y values, whereas this red line, these red lines will show the xx and yy values over here, xx and yy values over here. Let's make it a little bit more smooth. Instead of say 100 points, say I take the 1000 points. Okay. Okay, so then it will be more smooth. So I plot it again. Maybe I need to close it and then I need to run again. Yeah. So in this case, I get these data points like this. Okay. Interpolation. So what do you see over here? You can see that the interpolated points have been drawn almost by a straight line. So if you want an improved interpolation, then what you need to do is you need to specify what type of interpolation you want it. Okay, so even it is if it is 1000 points or 100 points, I think it will not much difference over here. So let's make it like say 100 points. Yeah, it is still the same. Okay, so where is the, yeah, if we want to make this plot smooth, then I think we should use some different type of interpolation. So here actually the answer is there, because in the interpolation command interp1, I have not specified what type of interpolation I want. I can specify it. If I don't specify what type of interpolation I want, the program assumes that I am wanting that the linear interpolation. So that's why it has simply linearly interpolated these points. So if I want a non-linear interpolation such as the spline, so I will input a parameter over here in the inverted commas as spline. So in this case, the program will apply the spline interpolation. Okay, the program will apply the spline interpolation. And now let's run it. So now you can see that it is much smooth. Okay, this spline interpolation is much smooth than the linear interpolation. And it's almost like a same like the sine x curve, original sine x curve. To compare how it looks like, how close it is to the original sine x curve. So maybe we can plot another curve, which can be say we can plot another one plot. Okay, we can plot xx, these the interpolated experimental values with the sine of xx. So this will give us the original data, and then let's plot it with the blue line. Okay, with the yellow, you can use any color with the yellow line, and let's see how it compares. So I will run it, and then so now I can see that I can only see this blue line, but I don't see any red line. Maybe the red line is hidden behind this blue line. So for this I can zoom in. So maybe I can zoom this portion a little bit. So I can see that now I can see a little bit of red color over here. I can further zoom in to this portion. Yeah, now I can see that red and blue lines are quite close to each other, okay? You see, if I'm further zooming it, so then I can see the difference. So this means that at a very high zoom level, these two lines are different from each other, but actually for all practical purposes, these two lines are quite close to each other. So what is our end result? So our end result is that this spline interpolation, which is in fact in the Matlab, the Matlab uses this third order spline interpolation. Okay, third order spline interpolation. So that means it shows that this spline interpolation is actually quite accurate. Okay, so this is what we have also studied when we were looking at these splines. So this spline interpolation gives almost quite accurate results to us. And then this we have also seen here in this example as well. Okay, so this is what I wanted to show over here. So do you have any questions regarding this? Hello?
No.
Yes? Do you have any question?
No.
No.
Okay, I think. Okay, then. Okay, so then this was the interpolation part. Okay, interpolation example on Matlab. So in which I wanted to show. So now let's see how we can apply this Matlab. So this trapezoidal rule on Matlab. Okay, so trapezoidal rule on Matlab. So for the trapezoidal rule on Matlab, how we can apply it? Okay, so I go to this Matlab over here, and let me show you the what we did for the trapezoidal rule yesterday. So trapezoidal rule we applied for two types. Okay, so single application or multiple application. Okay, so for example over here in your textbook, you have this here. And this is the single application of the trapezoidal rule. And then we have the multiple application of the trapezoidal rule. So for the multiple application of the trapezoidal rule, you can use this formula, okay? And when we apply this multiple application of the trapezoidal rule, we can get these values like this. So for the multiple application, we can have this. So let's apply this multiple application of the trapezoidal rule. So remember that yesterday we had this fifth order polynomial function, and we wanted to integrate it from 0 to 0.8 using the trapezoidal rule. And by taking only two segments, that is n is equal to 2, we found that the answer was 1.0688. And then we can further see, we can further see that if we increase the segments, the answers correspond to like this. So how we can reproduce it on Matlab? This is our purpose today. So for this, we can write a script. Okay, so let me write a new script. So we will start from we will start from n is equal to so for example, if we have this if we have this problem, okay, and then we can apply this rule, okay, the trapezoidal rule. So how we can start with this problem, okay? So we will start from a is equal to 0, and then what is b is equal to? What is b is equal to? 0.8. Okay, we will start from here. Okay, so let's assume we want let's assume we want two intervals, okay, n is equal to 2. Okay, so let's assume we want two intervals. And in this case, there are two intervals. So then what is the interval width? Interval width is equal to h is equal to b minus a divided by 2. Interval width.
I think you accidentally wrote 9 instead of the parentheses.
Yeah, okay. And then we can define the function, okay? So function is this. The function is this. So function we can define in terms of x is equal to 0.25, then we can write this function as like this. Okay. And okay, so now if we look at this formula for the multiple terms, where is this formula? Yeah, the formula for the multiple terms is that if we look at this part, okay, if we look at this part, the first term and the last term have coefficients of 1, but the middle terms have coefficients of 2. So therefore, what we can do is we can add the first and the last terms separately and the middle terms separately, okay? So what we can do is, because we have to find the sum, so I can say that our final answer I want to store in a variable is equal to I. So the first term of that will be equal to this. So our first term will be equal to f of a, okay, because this was the starting value. And for the next terms, for the next few terms, all of these terms will be multiplied by 2. So for this, what I can do is I can use a loop, for loop, and for I is the counter of the loop. And for this counter of the loop, I is equal to 1 to n minus 1. Okay, for I is equal to 1 to n minus 1. Then I can use, so suppose, okay, for this purpose, maybe let's take like 4 for the values of n, okay? So for I is equal to 1 to n minus 1, then what I can have is, so for example, now maybe in this case, like I will take 2, okay, So I is equal to 2 to n minus 1. Yeah, because 1 I is equal to first case I have already taken. For I will take the second case f. No, okay, I is equal to 1 minus n minus 1. Okay, and then what I will do is I will because the next value for the a will be a is equal to a plus h, because this will be the value for which I will evaluate the function, and then the sum of that value will be equal to this previous sum plus the new sum. The new sum will be 2 times f of a. Okay, 2 times f of a times 2 times f of a, and then I will end it. Okay, and then the one last term will be I is equal to I, that is the previous sum, plus the last term will be f of b. So in this case, it will work like this. So this time, this for loop will be repeated n minus 1 times, because from second term to the second last term, it will go like this. Okay, so then I will have this, and the final answer will be because we have to divide it by 2 as h by 2 as well. Okay, because in this case you have b minus a by 2 is h. Okay, b minus a by 2 is h. So b minus a by 2 b minus a by n is equal to h. So it is h by 2. Okay, so we have to multiply it by h by 2 as well, because you see that b minus a divided by n was h, and then there is 2. So they have to multiply it by h by 2, that final answer. So over here, I is equal to I into h divided by 2. Okay, so that's it. So in this case, I will get this value of I. So the final value of I can print it, and then let's save this as trapezoidal lab. Okay, trapezoidal lab. Yeah, I have saved it, and then let's
Sorry,
run this.
why is it
Yes.
lowercase I?
Okay, so my mistake. Yep. So I want, yep. Okay. Okay. So now let's see what is the answer. So for example, I run it. So it is 16.2368. So the answer is not correct, I think. Yeah, the answer is not correct. So I have made a mistake somewhere. So I took A is equal to 0, B is equal to 0.8, and then N is equal to 4. Okay, and then, yeah, oh,
In
okay.
H replace
Yes, it should be divided by N. Yeah.
N.
Yes. This was my mistake. Okay, so now I can run it again. Yeah, it is 1.4848. Yeah. So if we see that, what was the answer over here? 1.4848. Okay, 1.4848. So maybe if I want to say, like, for example, maybe for number 8, Okay, number 8. Okay, let's take, so now I can change n is equal to 8 over here, and then I run it again. So it is 1.66008. So what is the answer? It is 1.6008. Okay, so in this case, we get this answer. So in fact, we can make some changes into this script. So this was the basic core script. So maybe we can change, I have already prepared a full script in this case, and which gives us the values in the, so for example, in this full script, what I have is I start from this fprintf command, and then I apply 2 for loops, and then I take the values of n from 2 to say 100 at a spacing of 2. So let's see what are the results. Or maybe I take like the values of n from 2 to 10. Okay, 2 to 10. Okay, let's take 2 to 10. And this is the full script. So in this full script, I have added the error term as well. Okay, and then the fprintf command. So maybe now I can run it, and then you can see that now I get this table. Trapezoidal 2, so I get this 0.4 up to 0.08, and then a 1.553, which are the same values which I get, 1.615 and yeah, 1.615, 1.55, 34.85, 16.51, and yeah, 1.6. Okay, so we get the same values. So in this script, actually, I have used 2 for loops. So one for loop is for the values of n, and the other for loop is for the value of for the value of for the application of the trapezoidal rule. So that was the application of the trapezoidal rule for multiple steps. Okay. Okay. Now let's apply the Simpsons rule. Okay. So I think is it clear? Trapezoidal rule.
Yes.
Yeah. So what I illustrated to you first is the simple case for a particular value of n, and then I have later on I enclosed it and added some more fprintf commands to create the result in the form of this table. Okay, this is what that's what I have done. Okay, about the simple Simpsons rule. So that will be the Simpsons rule. Okay, let's apply the Simpsons rule. So for the Simpsons rule, we can also do like this. Let me open the Simpsons rule, which I have already created over here. Yeah, in fact, Simpsons rule we will study tomorrow in tomorrow's lecture. So here is this. Yeah. So there are two Simpsons rule. One is the Simpsons 1/3 rule, and the other is the Simpsons 3/8 rule. So I have done it for Simpsons 1/3 rule. You can do it for Simpsons 3/8 rule as well. And of course, we will look at the differences between these two rules tomorrow as well. So for Simpsons 1/3 rule, so I have applied this for loop first. So I took the value of for n from 4 to 2 to 20. So for different values, that means for different values of the number of segments. Okay, the different values of the number of segments. So for example, here we have these segments. So one segment, second segment, third segment. So different number of segments, this rule. And where is this? Yeah. So the same value, A is equal to 0, B is equal to 0.8. So for saving this space, you can also represent these on one line as well. So just put the semicolon, and then on the same line, you can define another variable. The h is defined as b minus a over n, and then here we have defined the function. And then we initiated the function by its first value. And for the application of the Simpsons rule, now you can see that here it is the difference. Okay. In this, inside of this for loop, there is the difference. Okay. So in this, for example, in the trapezoidal rule, it was like this. Yeah, it was like this. Copy, and let me, I will, maybe I can show you side by side. Control V. So this was for the trapezoidal rule. Okay, this was for the trapezoidal, and then this is for the Simpsons rule. So the trapezoidal rule, it is 1 to n minus 1. For the Simpsons rule, yeah, these for loop is different. For 1 to, with a difference of 2, and then n minus 2 you will take. Because in the Simpsons rule, in the Simpsons rule, we have to do, what we have to do is, we have to take two terms at one time. So that's why I will take an increment of 2. So here you can see that in this formula, I will take two terms at one time. So the even first term will be multiplied by 4, and the second term will be multiplied by 2. And then I will take a variable a1. That variable a1 will be multiplied by the multiple of this I times h. And in this way, its formulation will work anyway. So it is, the difference comes inside of this for loop. Okay, the difference comes inside of this for loop. So yeah, so it's here like this. So once it is done, the last term, the last two terms are also added separately. Okay, and then in this case, the integral, that is the sum value, is multiplied by h by 3. So here it is also the difference. In the trapezoidal rule, it was multiplied by h by 2. Here it is multiplied by h by 3. So that's why it is called as the Simpsons 1/3 rule. And then this is the error formula, and then f, this is for the printing the values. So if we apply this and run this command, then the results from the Simpsons rule are like this. So the results from the Simpsons rule are coming. So in this case, the results converge quite quickly compared with the trapezoidal rule. So let me show you the trapezoidal rule. So in the trapezoidal rule, if I run it, so now you can see the results side by side. So these are the results for the Simpsons rule. So for example, for the 10th iteration, the value is 1.640096, and the error is 0.0266. But here in this 10th iteration, the error is 1.55. The error is much more. Okay, so Simpsons rule is much better than the trapezoidal rule. Okay. So that was the Simpsons rule. Okay, in fact, yeah, so we will cover the Simpsons rule, the mathematics behind Simpsons rule in tomorrow's lecture. But this was the script for the Simpsons rule. So now next one is the trapezoidal rule for the uneven data. Okay, uneven data. Remember that in this previous trapezoidal rule and also for the Simpsons rule, we assumed that the data, the x values are even. That means from a is equal to 0 to b is equal to 0 0.8. The segments are of equal length. The segments are of equal length. So therefore, we can apply these rules. But however, but it is not always the case. Sometimes the experimental data which we get is not even. Okay, so this has been represented in this example. So after the application of the 3/8 Simpson 3/8 rule, which I am not covering it in this lab today, maybe I can give it like an assignment for you to cover it. This was the Simpsons 3/1/3 rule. Then there is Simpsons 3/8 rule, and then integration with unequal segments. So for unequal segments, the trapezoidal rule is more convenient to apply. We don't normally apply the Simpsons rule with the unequal segments. So if the data is with unequal segments, so we can apply this formula. Okay, that means we take the. In fact, this formula is just the separate addition of the areas of the trapezoids. So for example, if the first trapezoid has an area, has a width of h1, and then its average height will be fx0 plus fx1 over 2. So simply we can find the area of this trapezoid. And similarly, we can add up all these areas of the trapezoids of the corresponding trapezoids one after the other. Okay, one after the other. So in this case, we can apply the trapezoidal rule with unequal segments. So in order to apply the trapezoidal rule with unequal segments, what you can do is we can start a new script. Okay. So for example, we just take this example. Okay. So suppose we have this data. 0, 0.12, 0.22, 0.32, 0.36. So you can see that the spacing between the data is unequal. So for example, the spacing is 0.12 here, 0.1 here, 0.1 here, but here it is 0.04 here. That's 0.04 here. So unequal, it is an unequal spacing. So for this unequal spacing, so let's define the x values first. And in fact, I have already copied these x values. So I can paste these x values. Yeah, so x values, I have pasted it here. And we can find the corresponding f of x values by the equation, by the given equation. So the corresponding fx values are given by this. That means here, because we are doing it, we're doing the same for that this equation, fifth order polynomial equation. But remember that here in the previous scripts where we were using the equal uneven data, yeah, we were using these values. Okay, but here I am using a x as a matrix. Okay, in the previous case, so for example over here in this Simpsons case or the trapezoidal case, I did not use the for the power, I did not use the dot power operator over here. Although I can use it, it is actually always safe to use dot power instead of just power over here. Okay. But here in this case it was not needed because we were using the x values as scalars, individual basis. But here we are using these x values as a matrix. So therefore it is required that we take these x powers on the element by element basis. So therefore we will, for the power, you will use the dot hat operator over here everywhere. There is no need to use for dot star operator over here because 400 is a scalar over here. So for all the powers of x, we have to use the dot hat operator over here because the values of x which we have taken over here are we are taking it in as an array. Okay. So here the total number of x values are 11. So we will say that n is equal to 11. Although we can even use some function to calculate the number of elements of x, but let's do it, not do it now. So now what we have to do is we have defined the x and fx values. Now we have to add their areas. Okay. So for that areas, for first we have to just initialize the area. So we will take a variable in which we will save the area and then we will start from 0. And then we will take like for I is equal to 1 to n minus 1. Okay. We will use the sum which is equal to the previous sum plus now we will need to look at the formula. Okay. So the formula is this h1. And then let's take this 2 over here. So what is h1? H1 is the width of the segment. So h1 is the width of the segment. So for example, the width of the segment will be given by this. So for example, h1 will be over here, it will be equal to 0.12 minus 0. Okay. So that will be the width of the first segment. So that width of the first segment will be then given by this x xi plus 1 element minus the xi element. Okay, so this is the width of the segment. Okay, so you can see that, see from here is that this is the width of the segment. Okay, xi, okay, xi plus 1 minus xi. Xi plus 1 minus xi. Okay, so this is the width of the segment h1. So this width of the segment have to be multiplied by the average value of the function. So fx naught plus fx1 over 2, it is the average of the functions over these values. So average of the function over these values is equal to f at this value and f at this value. So this will be multiplied by, this will be multiplied by so this will be multiplied by f of x of I plus 1 and minus f of x of I. So now there are so many parentheses coming, so we have to be very careful for the parentheses. So if this is the main parenthesis, okay, this is the main parenthesis f of x of I plus 1, and then I need to close this parenthesis over here for this f, and then f of xi, and then therefore I need to maybe close this parenthesis as well. So therefore, this one, and then divided by 2. And then actually it is the average. So therefore, we need to put plus sign over here. Okay, so in this way, I have put these values. So and then here it is pointing out that I did not define I over here. So because actually I should have put it over here. For I is equal to n1 to n minus 1. Okay. And then this will add up all these sums. I will put end, and then in the end I want to print this value of the sum over here. Okay. So now let me run it. But for this, before running it, I need to save it. So unequal, that is trapezoid unequal in the lab. Okay. Yeah, so it has run it, and then it has given me the answer of 1.5948, which is the same as which we have got over here, 1.594801. Okay, 1.594801. If I format long, I can show more decimal places. So 1.494801. Yeah. Okay. So I can display it. Yeah, 1.5948. So in this way, we can use the trapezoidal rule with the unequal segments. So if you want, for example, to display these results in the form of some table, then you can make your changes according to your likeness. You can use the fprintf command with their appropriate formatting options, which we have done before, to print these results in the format. And then even if you can show the true error as well. Okay, so this was something about the coding for the trapezoidal Simpsons rule in Matlab. Okay, so do you have any question about this? Is it clear?
If we will be making a table with the results, so we also need like 2 for loops as in the trapezoidal, right?
Yeah, you can make the tables. I mean, in this case, I did not use any table to show it, but you can create, you can put the fprintf command at the appropriate location in the code, and then you can represent the results in the form of a table. Yep.
Okay.
Is it what you are asking or anything?
I mean, like in the code of trapezoidal, if I'm not mistaken, we use 2 for loops. One is for the function and another for the n.
Oh, yes.
Yes, it's
Yes.
here.
Oh, yeah. Yeah. So I think here you can. No, here you will only use the. There is no variation in the end because n is actually given by this value of this x. So number of data points. So these will vary. So it will not be. I think we will not need to use that second for loop in this case.
Oh, okay, thank you.
All right, so Okay, so any questions?